Good afternoon. When I grew up, my parents invested in my orthodontic treatment. Just like them, every year, parents of 5 million patients decide to spend more than $5 billion in orthodontic treatment in the US alone, and the demand is increasing continuously. However, despite its aesthetic and functional benefits, there are irreversible side effects such as caries, root resorption, and periodontal disease, which increase with the duration of the orthodontic treatment. Therefore, many therapeutic interventions have been proposed to accelerate tooth movement. The surgical approach, which is currently considered as the gold standard, is declined by patients because of the associated morbidity and the non-specific inflammation caused. We strongly believe that a more scientific approach would be to control the specific forced-induced inflammatory process by immunotherapy, which means delivery of drugs to empower the natural immune system. However, its use in orthodontics has still limited due to a lack of knowledge of the underlying immunological mechanisms and the rapid flush out of drug by blood circulation dictating the need for daily injections. So, in my thesis, we aim to develop a novel sustained-release drug delivery system based on immunotherapy and nanotechnology combined. Using an orthodontic mouse model and RNA sequencing, we reveal the full map of the genes affected by the mechanical force. More specifically, we identified the bone resorptive cell, the osteoclast, as a crucial factor during tooth movement, and therefore we selected its activating ligand, called RUNCL, as an immunoactive agent in our system. Or, in other words, we aim to use the osteoclast as a biological knife in our system. But the real challenge was how to deliver a drug over a long period and restrict its release locally. For this, we engineered unique liposomes, which are artificial human cells-like vesicles. The liposomes were loaded with RUNCL and embedded in hydrogel to enhance the local effect. But if you have something good, why not to multiply it? So we encapsulated a few liposomes in one large vesicle, hence increasing the total amount of drug and its local effect. As a proof of concept, a single injection of our formulation in the orthodontic mouse model resulted in more than twofold increase in the distance of tooth movement after 14 days without any systemic effect, which was incredible. So, in conclusion, we successfully developed a novel sustained-release drug delivery system which dramatically accelerated the orthodontic tooth movement. But it's not all about orthodontics, so we wonder, is it possible to use this platform in other medical fields? Our preliminary results say yes, but further studies are still needed. Thank you. Grand finale.
Question.
Thank you, Yehuda. This is so cool. And I'm an oral surgeon, so I know what you're doing, and I know
we can
it's
talk
amazing.
about it after. Yeah.
Well, I have two questions. First is, how long does it last? Did you able to measure how long does it control the release, like 2 days or 3 days or 4 weeks?
Yeah.
And second is, where did you inject? Is it like around the root or like in the periodontal pocket? Where did you inject?
This is later. Okay, thank you.
Thank you.
Okay. So, first question, we found that the release were up to 14 days, compared with the saline control with takes something like less than 1 hour. So this is the first thing. And second, we injected it around the first molar, as you can see here, around the first molar and under the gingiva. Okay, so and it diffused for all over around the teeth and all of this.
Okay.
Thank
Very
you.
good. Thank you.
Thank you, guys.